Sie irgendwie Probleme haben oder so, können Sie mich gerne anrufen. Meine Filmkastennummer haben Sie ja, nicht?
Ja, auf jeden Fall. Ja, ich hatte versucht, in der Zwischenzeit Ihr Handy anzurufen, aber da hat sich keiner gemeldet.
Bei meinem Handy?
Ja.
Nee, das habe ich auch ganz selten an.
Sie hatten mich da, als wir letzte Woche in Hamburg waren, hatten Sie mich kurz angerufen. Ja, und
Okay.
ja, deswegen hatte ich die Nummer noch. So, we will continue. We have to calculate of one winding the reactance. And we have two parallel conductors. Left we have A and B parallel, and another conductor is CD parallel. And we have to calculate the reactance of the whole winding. What we have to do. So, we have first is, all times the first is to calculate the GMR. So, the conductor A and B and C and D are the same. So we have to calculate GAA. GAA. How to calculate GAA? GAA. So, now we have to look in the formula list. Where is the formula list?
You see, this is this example. Two parallel tubes. You see that here and here? Yeah? This is the example, this exercise. This is from the system, old system with tubes. Yeah?
So,
this is the example. Here are two parallel tubes, here and here. You see that?
so
This is maybe an example shown here.
we have the outside radius
Okay.
and we have the inside radius. The outside radius is R2, and we can use this formula here. We have to notice this formula. This one. I will put here R2 minus
Question, was passiert? What happens if R2 is identical then with R1? What happens if R2 and R1 are equal? Wissen Sie das?
Na klar.
You know
I think the question is not to me, I know it. The situation is shown on this presentation.
Was passiert denn? Der wird doch, da besteht eine Null im Nenner.
That's no problem.
Then?
Then you have to use the rule of the L'Hopital, and then you will.
Yeah. Das ist lange her.
I thought Mr. Tim want to know the value which we get then. And that's easy. Then it's very small. Then we have this one, and then we can use this formula G11 is R.
Yeah. But how is the way? How is the way to this?
Yeah, you have to.
L'Hopital'sche Regel.
The way is you have to build the logarithm of this, and then you have to use L'Hopital.
L'Hopital'sche rule, the rule of L'Hopital. Because it's not allowed to divide through zero. You know that my question, what the reason my question is.
But I tell my students,
if these are equal, this is zero. It's not allowed to divide through zero. And he says, I know this. L'Hopital, she has a rule of L'Hopital. You must make a differential equation.
No differential equation. That's a Taylor law. L'Hopital is to divide some expressions who are zero or indefinite. And if you make a Taylor law, you will get the zero terms, and then you will say if you have expressions 0 by 0, divide by 0, you can say it is the result is the derivatives at this point have to be divided. And then you will get this. But I will tell my students in every time what you have to do if you're not mathematical, not so clear. You will put in 3 millimeters and 2.999999 millimeters, and then you have to see what will happen. It's a possibility.
Okay.
So, we have often to look in the table of formulas. And this is what I give you today and tomorrow. It's the abstract of the importance formula. The book is very big and it's not so abstract of formulas. Okay. Now we will get back to the exercise, what we have to do. So, now we have VAA. Now we have to calculate GAB. But it's easy. It's B. It's 300 millimeters. We have GAA, we have GAB. And how we get now G1. G11. Which value has G11? I know it. I ask you. Perhaps we may look in the formula, or yes. GAB, yeah. What to do with? No? Good. Yes. We have to put in these two values, and then then we have a value in millimeters. We will look what it is. G11 is 96. So it's therefore 1 millimeter. So then we have G11. The next step we have to do for reactance calculation is G11 we have first was G12. What is G12? We have already had, if we look C, yeah, AD, yeah, and BC, So I will input this. We can look at AC is 800 millimeters.
Yeah.
AD is 1,100 millimeters. BC is 500 millimeters. And we have BD, we have 800. And fourth. So, when we get here a value, the value is 1, 2, 9, 0 millimeters. Now we are now we have the same. Now we have. Now we have the same as this here. This problem here. This problem has G. This is only one conductor and not two parallel. Here we have two parallel conductors. They are parallel. And we have here G12 and we have G11. Now we have a G12 and a G11. And so the problem is if you have parallel conductors or you have copper plated electrode arms, you have to calculate the GMR. And if you have the GMR, you can calculate the reactance like this. And if you only have in the first step to calculate the reactance between these two parallel. And that's important. If you have 1, 2, 3, 4 parallel, tomorrow I think tomorrow we will calculate the electrode. It's the same as you have a Kupferkasten, was heißt das?
Was?
Kupferkasten.
Coverbox.
Coverbox for the transformer. But the principles are the same. You have to calculate the GMR of one conductor. And with this, if there are 4 parallels, you have common for all four conductors. So, and if you have now these values, you can go into the next formula. You have to go to the formula. You always look for formulas. So now you can calculate x11 and x12. x12 with these values here. That I will do x11. That are two methods, and I think they do not differ so much. The calculation with approximation, I take the without approximation, and x. No, that's no calculation with approximation. With approximation, exact calculation. x11.
1, 2. This means 1, 2.
That's 1, 2.
Yes.
Milliohm and 1, 1.
Yeah.
1, 1. If 1, 1 is 9 million. So now you have this reactance, and you have to put together. X is x11 plus x12 plus x21 plus x22. This is x21 and this is x22.
This is minus.
Minus, I forgot. And minus.
Yeah.
Okay. And then you will get x is 2. This one. 1 minus. So then you have this side. So this is there more parallel. Oh, I have to look what is the next one. So, that was this next is an exercise for you. But I think if you calculate this, we have finished for today. But I explained this. If you want to calculate, you can do it if you're at home. And I will come to the next. So, next example. So I will C, D, B, E, G, we have here the y 1, y 2, with currently 1, with currently 2. So, now what have we to do? We have to calculate x11, and x12. x11 is the self-inductance of a loop, and x12 is the mutual. So what have we to do? In the last example, we have calculated self and mutual reactance for this one, or this one. Now we have a complete loop. This is the first we have complete loop. So, easier to understand, normally 1 to 2. x1, 2. We have already done, but we have to do it again. x1, 2. And we have already current direction, current direction, current direction, current direction, current direction, current direction. So, x12 is XAE plus minus SAH. Next one is G
plus. This plus.
C is plus. Yes.
minus XCF
CF.
minus XCP.
No. No, we have this to 2. If and in the next time, if we calculate x11, then we have 2. So we have A, C. Now we will consider D. DE is minus plus
H.
H, yes. Now we have finished D.
Plus.
XPF minus XPG. EG.
Well, now we B.
PF.
Okay. So 1, 2, 3, 4, 5, 6, 7, 8.
VG.
Minus BG and BF is positive. Okay, is 8 okay? A1 and A has 2.
Yes.
A has 2 and everyone has 2.
Yes.
So we have 8. And it's a logical that we have 4 plus signs and 4 minus signs. 1, 2, 3, 4. Okay. So that's 1, 2. This is 1, 2. And now we have x11 to calculate. XAA, XAA,
Yeah. SBB is
it's correct, but if you want to make no error, I would say we begin with A and make to D, to C is 0.
Yeah.
That's normally I have here to say X, A, C, and so on. But it's 0. That means we start again. One bit A plus
CC.
XCC plus BB
Yeah.
plus BB
Yeah.
XBB
Minus
minus
SAB
XAB
minus XBA 2.
Okay. 2.
minus
2 is CB BC.
BC.
This.
It's correct that we have 8.
Yes.
1, 2, 3, 4.
5, 6, 7.
Okay, and then we have 4 with plus and 4 with minus. That's correct. So, so
Okay.
it's the next one for you.
Okay.
But do not look
Okay.
on this paper. I- Dann haben wir das Kapitel 2 auch schon finished. Dann the Chapter 2 ist finished. Ich denke, wir sind zu schnell.
Ja.
Aber wir sprechen morgen noch die ganzen Beispiele von den Öfenbeispielen. Wir sind ja noch nicht beim Ofen angelangt.
Nein, nein.
We not saw any
The furnace.
furnace. We had only simple examples now.
Also wenn Sie morgen Kaffee brauchen, 2020 muss es eingewählt werden. Steht da oben. Ja? Dann nehme ich mal wieder weg. Die ist ja nur für Fernbedienung. Die brauchen Sie ja nicht.
Die waren
Ich tue sie aber hier mit rein in die Box. Ja?
Ich weiß noch, dass Herr Tippken einmal so ein Seil durchgerechnet hat, was da rauskam. Die Unterlagen, ich weiß nicht, wo die geblieben sind, also das wollte ich auch noch mal alles mal nachrechnen. Und aber da hat man keine Zeit zu.
Nein, aber das habe ich Ihnen ja erzählt, dass er auch Mathe-Professor geworden ist, nicht? Tippken.
Ja, Tippken, Bernd Tippken war er.
Ja, der hat irgendwie, ich weiß nicht, Wirtschaftsingenieurwesen studiert, glaube ich. Ich weiß es nicht genau.
Nee, der hat Mathematik studiert.
Mathematik, ja.
Oder Physik, ich weiß es nicht.
Er war ein ganz cleverer, nicht?
Der war clever, ja.
Das merkt man als Mitarbeiter ja eher als Hochschullehrer, ja.
Wissen Sie, wo die Ulrike geblieben ist? Die war ja auch zusammen mit ihr da.
Das weiß ich nicht. Wie hieß sie noch?
Ich weiß auch nicht mehr, wie die hieß. Also ich weiß bloß, dass sie Meteorologin war.
Ja.
Und Alexander war auch da. Also der war auch
Block.
Nee, der war später da. Alex, ein großer. Der Block war klein.
Mhm.
Kann das angehen, dass der in der Anwaltskanzlei gelandet ist?
Nein, das glaube ich nicht. Block war der zweite Physiker neben Herrn Griegert. Mit dem hatte ich so seine Schwierigkeiten, weil der nicht so wollte. Der hat ja Spektroskopie gemacht. Und
that's the solution. But you can see that. Okay. Did you have questions? So, chapter 2 finished. We are very busy today. But if you have questions to chapter 1 and 2, and to the examples and so on, you have to ask. Otherwise, we are finished too early and we have not learned enough. So, step by step, we come to the furnace. And now we have to make chapter 3. Chapter 3. The next presentation, chapter 3, is many of mathematics. But I calculated this and then I brought it into the paper also. But what you need is this what I gave you. Okay. What is a stripline conductor? A stripline conductor, if we have copper plated electrode arms or copper boxes in the transformer line, we have to calculate this geometric numerator, this geometric numerator. I would say first we can consider this, and for this we have to consider, for example, this to this, or this to this. That means this to this is this to this, and this to this is, for example, this to this. We have to calculate strip line conductors. That means we have high current suppression, displacement, high current displacement. The current flow is only in 1 centimeter, and the electrode arm is 600 centimeters, and then 1 centimeter is 0. Then we have a strip line conductor, and that's easier to calculate. And this chapter 3 calculates this to this, or this to this. Therefore, the formulas. In this paper, the derivation of these formulas are given here, with integrals and so on. But I think if I wrote the program, I have once calculated the formula, then I have programmed the formula, and then never used the formula again. Then came Posco and said he wants to have theory, and then I calculated it again and transformed all the things in English. So we have here perpendicular strip line conductor. What are perpendicular strip line conductor? I will. If this is phase A and phase B, you have to calculate, for example, this to this. This to this, you have to use the buffer. And for example, if you have to calculate XAB, if you want to have XAA, what you have to do then? You have to use this to this, for example, with a part conductor. And if you have this part conductors, you have to use this formula below. Yeah. Because there are some values 0. And if some value is 0, it's easier to calculate. So this is a problem. This problem is not shown here. If we have this against this two strip line conductor, then one value is 0. Is 0. I will explain over that. Ich komme mal wieder durch. So, GMR calculation is always a double integral. What to solve. And you have to put in limits. This limit, this limit, this limit, and this limit. In f von x and epsilon. Here is a formula, and this is the same as shown before. You have to put the values x and epsilon 4 times. At this place, at this place, at this place, at this place. And therefore, you have a subprogram then. This one, and that you have to put in 4 values. 4 values, and what are the 4 values in coordinate points? The 4 values of coordinate points are 1, 1, this coordinate point, 1, 2, and 2, 1, this coordinate point, and the coordinate point. And if you have the same index, you have to add, and if you have the different index, you have to subtract. And here you see the geometric mean value is we have to divide by the length 1 and the length 2. The Neumannsche Doppelintegral we have to say by area 1 and area 2, but if we have a strip line conductor, area goes to the length. And you have to
This means L1 and L2 is this x line, x1 to x2
Yes.
length.
Yeah. And if one value is 0, then this expression to divide by 0, it's not allowed. Then you can make a calculation with the L'Hopital and then says this expression is 0. But if you put in 0, the program will say, oh, I can't do it. Therefore you have to ask. So, and you have to put in four times the coordinates. But this is a lot of work. And I made a lot of examples for EIF calculation of electrode arms. And that's a long part of the book, and I think we will talk about tomorrow about this. But now we have to talk this normally formulas. This is for example, for this case. And for self-reactance, we have this formula, and we can calculate it out of this. It's this formula to put in B and A, and if you have only to put in one coordinate, and that would be in this place 2 and 2, because this coordinate is 0 in x, and this in y. And so we have only to put in, we have to overtake this formula with h and b. It's easier to calculate this as this. Therefore, I noticed this. So, the next one is the following. If we calculate,
In this case, we have two formula, but in our program, we have two formula. We can use the formula. We can use the formula in our program.
the
To apply to the two formula.
the program, in the program, you have only the possibility of full-plated to full-plated, to full-plated, full-plated to half-plated,
Und dreiviertel geplattiert.
and
In den Außenphasen.
full-plated to three-quarter, and three-quarter to half-plated. And the program, what does the program? I programmed a long time ago. What you can do is to ask if smaller than 1 millimeter, then set it to 0, and the result is 0. So, if this argument in this formula is smaller than 0.1 millimeter, for example, then set it to 0, and then we will get put out 0. And if was heißt Betrag auf Englisch? Absolute
value.
Absolute value. If the absolute value, not the value is less than 0.1 millimeter, the absolute value is, it can be negative. Then you have to put in 0 for the result, and you have to add here nothing. And if that is not, you have to put into it the value. But if you have this one, you can easier use this. So, this is perpendicular. And now we have to look for parallel. Parallel is, for example, this and this. Parallel is this and this. Parallel is this and this. And so on. And therefore, we have formulas too. That is the normal formula with here have double integral gives 4 limits you have to put in, and there's so that's a normal formula, and with you have in this formula the difference between U and V is interesting. You have always to put in this the difference between U and V, and if it's 0, if it's 0,
Hallo? Wollte ich fragen, ob alles soweit passt oder ob Sie noch was brauchen?
Also ich hätte gerne noch einen Kaffee. Also den Kännchen Kaffee.
Ja.
Möchte jemand noch was trinken?
Water? Coffee? Tea?
Coffee?
Kaffee?
Ja.
Ja, Kaffee. Zwei Kännchen Kaffee.
2 Kännchen Kaffee?
Ja.
Bestimmt okay.
Die alte können Sie nachher mitnehmen.
Zum Start.
Okay, ich lasse es ein bisschen eingelehnt.
Müssen Sie nicht, ich habe eine Karte.
Ja, Sie dürfen aber so reinkommen. Ja,
Dann
dann
darfst
müssen
du
wir nicht klopfen.
Okay, perfekt, so machen wir es.
Okay.
So, you will get coffee. And that's the same. We have a formula, we have to put in 4 times the values, and we have 4 coordinates in U and V. And then, if we have this one, this to this, that's this case. And if then you have, it's very easier than here. Then you have an easier formula. But this is a lot of theory. You don't know why should I calculate it. But if you now have one geometric mean rate GM from here to here, you can combine it with the other. And then you can, for example, calculate this to this. That's the aim, this to this. So the aim for tomorrow, I can show you. The aim for tomorrow is that we discuss all these examples. For example, coplanar, such this one, this one, and all these examples we have to do tomorrow. But this is first we have to do this theory. And
in this case, we connect same.
this is the same.
And this area.
Yeah, you can put it so. The program calculates it with negative values. Then, but if you put in negative values and do the change, it becomes the same way. It becomes the but you have sometimes you have to turn. Yeah, and next time I have to show you how to combine this. But I think it's not shown in the book. I will show you on paper. So this was one part conductor to another part conductor, and if you have one, you can calculate the geometric mean radius of a copper-plated electrode arm by this formula.
We have all these examples in the program. You know, if you have a special design of an electrode arm, we can use the lower for outside phases, in the middle for the middle phase, if you want to save money. I do not know if they make this today in furnace development, but we have calculated this before, because some years ago they have made some construction, but in most cases they use the upper example, because we don't know what happens with magnetic fields in the iron part. If there's no copper plate on it, we don't know this. But it seems that it works. But many people also ask, oh, this is too expensive. Or let's use this for the middle phase, this for outside phases. And some people also have asked, can we also use a solid steel system, a steel without copper protection? We do not know this exactly. What happens in the steel? If there are too many currents flowing in the steel and heating the steel up, we do not know this. Because the deep the Eindingtiefe skin depth is much smaller because of the permeability of the iron.
But if it goes into Zentigo, what's Zentigo?
In saturation, the iron is going into...
In this case, first we use in this upper side this general type. Second and the third, we can use this type of tube. So in this case, some only save the money, and the other case is some problem or nothing, not problem.
We don't know if these construction give problems. We don't know that. You can measure it on the temperature of the cooling water. You can see that. But it is not easy to make solution, to give you solution of this. We are not the same opinion. I say, do you always use this because you are on the secure side, and others is also saying you can use a pure steel system.
Because separation?
Yeah,
Saturation of the iron. And then the permeability is very small, and then the skin depth is bigger than copper. But normally, if no saturation, the skin depth is very, very small. But we don't know.
the same question is how deep, how thick is the copper? Shall we say 6 millimeter or 8 millimeter? 9 millimeter is not necessary to make more than 9 millimeter, because if you have more than 9 millimeter, there's no current flowing in more than in 10 millimeter. 1 millimeter is too much, and most I think are about 8 millimeter or 7 millimeter. It's dependent from what the customer likes to pay. Yeah. But this company, like Mr. Elliot from Fuchs, they invented this system of current conducting arms. And this is state of art since 1984. This is the state of art to use current conducting arms. Yeah. And nobody before wanted to take the risk for this construction. Many people said, no, do not use this. You can imagine.
But the same is with no copper plated.
Yeah.
That the current is flowing in the iron. Nobody knows if it works. It may work, it may not work.
And also, what happens if you make wie heißt Edelstahl?
No magnetic steel.
Not magnetic steel. What happens then? But it is not good to weld for welding, yes? Not magnetic steel. We do not know, but this is you see the development is not at an end. But if you are building these constructions, you may make an attempt with your own risk.
If it works, you are the greatest. If it not works,
Ja? Komm hier rein. Okay. Oh, wir nehmen also viele Tasten mit. Das ist ganz prima.
Vielleicht mag ja auch noch jemand anderes.
Ja, wir nehmen das mit. Wir sind auch sehr zufrieden.
Perfekt.
Wir waren noch mit dem Mittagessen.
Also
Ja, das reicht auch völlig aus.
Okay.
Man braucht da gar nicht mehr.
Ja.
Das ist eigentlich eine gute Lösung. Ja.
Okay. Dann machen wir es jetzt gern immer so,
Ich bin
beziehungsweise.
morgen nicht da, morgen ist der Alas da, und wenn er Kaffee braucht, ruft er Sie an, oder 2020.
Genau. Wir können es auch gern so machen, dass ich einfach einmal vormittags und einmal nachmittags vorbeischaue.
ja, die Zeiten 10:30 Uhr.
Ja,
Genau.
um 10:30 Uhr und um 15 Uhr.
Genau, so
Okay.
machen wir es.
Können Sie ruhig von selbst reinkommen.
Okay,
Sie dürfen auch sofort reinkommen, brauchen nicht zu klopfen. Ja?
Okay.
Okay.
Wie sollen wir es denn mit dem Geschirr machen? Sollen wir das einfach dann morgen früh mitnehmen oder sollen wir heute Abend nochmal hochkommen,
Das
weil Sie
Geschirr?
Bescheid sagen?
Also Sie können auch hier reinkommen, und wir gehen heute Abend weg. Ja? Sie können auch das wegnehmen.
Sagen Sie mir gerne Zeit, dann machen wir hier ein bisschen sauber, stellen Ihnen auch gleich ein paar frische Gläser rein für morgen oder für die Tage.
Das müssten Sie sagen.
Ja, 17 Uhr. können Sie hier reinkommen.
Okay, perfekt.
Wir lassen aber die Technik hier so
Das
alles
ist überhaupt kein
stehen.
Thema. Wir gehen nur kurz rein, nehmen das dreckige Geschirr raus und schon mal ein paar frische Gläser vom
Ist
Boden.
in Ordnung für dich
Ja.
gut? Gut mit dem Service? Wir werden vielleicht dann auch wiederkommen.
Das wollen wir gerne hoffen, ja.
Ja, okay.
Okay, noch einen schönen Tag, ja.
Okay.
Ja, danke schön.
Thank you.
Yeah, please take your coffee.
Yeah.
If you want to have a coffee, there are enough coffee cups.
Mhm.